So I want to come right out of the gate and say that the title of today's talk is way bolder than we're able to prove or, or rigorously justify, but it's supposed to make us think about the conventional wisdom of how we use the fundamental equations of fluid motion. So I've very rarely not given a talk. I've very rarely given a talk that didn't start with the Navier-Stokes equations. And today will be another one of those talks where I do start with the Navier-Stokes equations. Here they are. These equations, 100 years of experience tell us that these equations, to the best of our understanding, reliably predict, describe the motion of a fluid in a certain regime.
Could you explain how the preference depends on how is it given or how do you get it?
The pressure?
Yes.
Right. So you can recover the pressure from the velocity field by taking divergence of this equation, and then Laplace P solves an equation in terms of U. So you can find the pressure this way. So yeah, U is the velocity field, P is the pressure, F is a body force which acts everywhere in the fluid, accelerating or decelerating fluid particles. First equation is Newton's law, F equals ma. The second equation is incompressibility, which I'll explain in a second. But these equations, we say they describe fluids in a certain regime. Most of the time when we mathematically work on these equations, we suppress all these adjectives, which I want to bring to light, just so we remember they're there. So first of all, Navier-Stokes equations are a continuum description of a fluid. These are homogeneous, which means constant density. Constant density is preserved when the equation is incompressible. Incompressible means that if you have a parcel of fluid which travels, it gets flowed, its volume is kept. Its volume doesn't change. Incompressibility is said to be a good approximation in the low Mach number regime, which means that the characteristic speeds of the flow are much smaller than the speed of sound through the fluid. And lastly, we assume that temperature variations are negligible. So in this regime, and maybe there's something I even forgot. Most of the time we suppress this, but in this regime, the conventional wisdom is the following. The state of the fluid at future times can in principle be predicted from the state of the fluid at the initial time by solving the PDE. And I make no claims that we should forget the conventional wisdom, nothing like that. But we as mathematicians, when we study these equations, we try to understand, in a precise sense, when you can use these equations, when they can't, when the conventional wisdom holds, and when it doesn't. So in this conventional wisdom, I talked about solving the PDE. How do you solve the PDE? When can you solve the PDE? You can develop heuristics about when you can solve the PDE from dimensional analysis. But first of all, we note that Navier-Stokes equations has this number nu. This is just a positive number. It's called the kinematic viscosity, and that it's a dimensional constant, which depends on the fluid. It is dimensions of length squared over time. And whenever you have a dimensional constant, for example, the speed of light, you can use it to relate to different kinds of dimensions. So for example, a light year is really a measure of length, right? So in this way, you can use nu to relate length squared in times if you treat this as dimensionless. So in this dimension counting, x is units of length, t is dimensions of length, t is dimensions of length squared. So u, which is a velocity, typically dimensions length over time, in this counting has dimensions length inverse. At a mathematical level, this dimension counting is realized in this scaling symmetry of the equations. If you have a solution of the Navier-Stokes equations, you can get another solution by doing this rescaling. This lets you zoom in or zoom out on solutions and on data. So this zooming is going to give us heuristics about when certain terms in the equations might dominate and when solutions are smooth, etc. It turns out that critical spaces, X, those are the spaces whose norms are invariant under this rescaling procedure. You can also think of these norms as dimensionless quantities, or they have the same dimensions as nu. So examples of critical spaces are LD if we're in dimension 3, or weak LD. And in fact, the heuristic I want to present is even clearer in this weak LD space. This weak LD contains functions that are like 1 over x, or let's say like sigma over x. When you plug such functions into the equation, you have this Laplacian term, which behaves like sigma over x cubed. And you also have the u grad u term, the initial term, which is like sigma squared over x cubed. So when sigma, the size parameter, is small, you expect that the Laplacian will dominate. You can solve the equations. You can find and things will be well posed. When sigma is large, you expect that the nonlinearity will dominate, and maybe you can't solve the equations. So this heuristic suggests a regularity threshold in terms of these critical spaces for when you can find, when you can prove well posedness, when you can find, at least locally in time, that there's a strong solution unique within some natural class and smooth. Okay, there's a kind of general classification of PDEs. Actually, you can find this discussed. There's a general meta theorem known among practitioners of PDEs, but you can find it discussed, for example, in Kleiderman's article "PDE is a Unified Subject." And what you do is this. The way you think things is this: given a PDE, there's typically some conserved quantities or some a priori controlled quantities. And you look at, in terms of regularity, the strongest known a priori controlled quantity. For the Navier-Stokes, it's the kinetic energy. Okay, this isn't really the kinetic energy. Sorry, I should square this and divide it by 1/2. So this norm is controlled a priori. It's our strongest known coercive quantity. But this norm lies below the regularity threshold, which would guarantee that you can control the solution and prove it smooth. So in that sense, we say that Navier-Stokes is supercritical, because the strongest norm that out of the gate you control is supercritical, lies below this regularity threshold.
So sorry, what does below mean in terms of scaling? It means it.
So let's just say L. So if L3 is a space that lives on this threshold, L infinity would live above and L1 would live below. So in terms of scaling, these spaces which live above, which we also call subcritical, are ones whose norms decrease when you zoom in.
Okay.
Zooming in matters because regularity is about small scale behavior. So you zoom in when you want to look at it. So that, and supercritical quantities, when you zoom in, their norms grow.
Do you think about things in terms of like finite volume or periodic solutions? Like, should we worry about the fact that,
that real fluids don't take up the whole space?
Well, I mean, the LP spaces aren't ordered normally, right? But
right, that's right. I would say that we normally don't, but they're not ordered because they capture two kinds of behavior: local behavior and far field behavior. For regularity, we're worried about local behavior, and then we order them. Yeah. By the way, I love the questions. So thanks. Okay, so we don't know. It's a famous open problem about whether solutions of Navier-Stokes remain smooth globally in time. But we do have a notion of solution that at least exists globally in time for reasonable initial data. These are weak solutions. Actually, we give them a name, Leray-Hopf solution, which recognizes the fundamental contributions of Jean Leray in this 1934 paper, and Eberhard Hopf in his 1951 paper, when he treated the case with bounded domains. A modern version, a modern statement of what they proved, and which includes a body force, is the following. For each initial data, or for each initial velocity field, which belongs to L2, is divergence free. And for every force belonging to L1, L2, there exists a global in time weak solution, which we call the Leray-Hopf solution. It satisfies various conditions. So one that I'll draw your attention to is this energy inequality. So this says that the kinetic energy at time t plus all energy we know has been dissipated through the viscosity. So you can incorporate a nu here. Typically, I'll rescale nu to 1. But these energy quantities are controlled by the initial energy and the contributions of the force. So this quantity on the left-hand side is a priori controlled. And the guarantee is that U is controlled in this function space. L infinity time L2x intersect L2 time H dot 1x. This dot means we're just measuring gradient U in L2. So these weak solutions, they satisfy this energy inequality. But Laray's approximation procedure actually produces what we now call suitable weak solutions. I don't really know the precise history of this term. I think it first appeared in a paper of Kafferle, Kohner, Nierenberg in 1982. I would like to know more about how they chose the name. It sounds kind of ad hoc, like we'll just call them suitable because it's working for what we want to do. In any case, these solutions, they satisfy a slightly more refined version of energy inequality. They satisfy a local variant. So with these suitable weak solutions, you can say something more. At least when the force is, let's say force is 0, force is regular enough, you can prove partial regularity. Partial regularity in this case means that the one-dimensional Hausdorff measure of the singular set is 0. So these solutions can't form singularities on the line.
What's P1? Is that just Hausdorff?
P1 it's because this is really parabolic Hausdorff measure where you're covering everything with parabolic balls.
Yeah,
That have-
space-time.
Yeah, in
And the
space-time.
singularity means not C1.
So singularity, so you can, there are many equivalent definitions, but let's just say where the solution is not locally bounded. A point in spacetime is a singular point if you cannot draw a ball around it in which it's bounded. Okay, here's the schematic picture of almost the current understanding of the regularity theory.
Sorry, could you just say one word, how you proved that, how you proved this global in time,
This,
the Leray-Hopf?
right, so you multiply at least for smooth solutions, you multiply the equation by u and you integrate by parts. This term here, this will drop out in the integration by parts.
Oh, sorry, not the inequality, but how do you prove there exists this global in time?
Right, great question. So what you would do, I mean, there are different ways to do it, but you want to regularize this equation somehow because you're working with supercritical data. And so what Larray did at least is you take this U here and you truncate it to only low frequencies. So you remove some of the frequency interactions. You apply a modifier to this U here. And then you can still prove the same kind of a priori control on energy. So then at the modified level, you get a global in time solution, and then you can take the modification parameter to 0.
To modify, you make a convolution.
You make a convolution with the test function, yeah, at scale epsilon. So, but there are other ways. Like if you're on the torus, for example, then you can expand. You can expand in terms of sines and cosines. Just truncate that. So, or you could do something. You could add. Laplacian squared. There are many ways you could go about it. Not all of them will guarantee the local energy inequality, but Laray's procedure produces this inequality as well. So the schematic picture of almost where the regularity theory is these days is the following. Let's say you assign some initial condition which is nice enough in a subcritical space, say H1 is subcritical. Then at least for some time, there's a unique, what we call strong solution, and all the weak solutions agree with it. So there's one solution, basically. It's instantaneously smooth. And then you evolve this using the PDE for some time. Then there's going to be, you try to understand whether the solution can lose smoothness. So let's say there's some time T star, which is the maximal time of smoothness. I mean, the millennium problem is essentially something like, can T star be finite? If T star is finite, you can say something about what happens at a singular time. You can say there must be point singularities around which the solution wants to become unbounded. These point singularities can't concentrate on a curve. And moreover, after this time, you can continue the solution, not as a strong solution, but as a weak solution. Weak solutions become relevant if the strong solutions break down. If the strong solutions don't break down, then you contain yourself with strong solutions. Everything agrees with that.
One thing I didn't, you start with something like L2, but immediately it becomes infinity because kind of it equals.
That's exactly right. That's exactly right. Yeah. So it must be a little better than L2. Let's say H1. So bigger than H1/2 will do. or L3 will do. Okay, I want to, most of the talk is about you know, what could go wrong with weak solutions, but we should start off with a success story about weak solutions that might give you some hope or motivation for considering them. So the successful story is the case of scalar conservation laws. And for example, let's just consider burgers, make life easy. Consider Burger's equation. This is essentially the same, if you like, same nonlinearity as Euler. And here we're doing, let's say, no viscosity. So it's well known that, you know, if you start from smooth data, then, you know, you can develop a shock in finite time, lose smoothness. Solutions would remain bounded, but lose smoothness, become discontinuous. In spite of this, for every initial data in L infinity, there is a unique weak solution that, you know, exists past the shock, and this notion of entropy solution. We don't have to go into the precise details, but I'll also note that if you regularize the equation with the Laplacian and you take nu to 0, then these solutions converge to the unique entropy solution. So in this case, despite the fact that there's singularities, you can continue past them and not be so concerned. I want to mention, however, if you regularize the equation in a different way, for example, if you study KdV and you take a small dispersion limit, this is a dispersive regularization, then the limiting solutions need not agree with the unique entropy solution. So this was studied in detail by Lax and Livermore in the 80s. So you can think of this regularization, for example, as a toy model of trying to add more fundamental physics to your problem. And the weak solutions you're interested in, you hope, come from more fundamental physics. In the case of Navier-Stokes, there's been mounting evidence that points toward the expectation of non-uniqueness. For example, in 1969, Olga Lazinskaya constructed an example of non-uniqueness for Navier-Stokes within a Luray-Hoff type class. There are a few caveats, though. So first, let me say the caveats first, then we'll read the quote together. The first caveat is that the construction is in a domain whose boundary is changing in time. And as time goes to 0, the domain shrinks self-similarly to a point, shrinks self-similarly to nothing. Her example also has
but there is no density. No.
Well, her equation is really kind of an odd toy model. So it is Navier-Stokes, but in this domain. And the boundary conditions typically you would use no slip conditions, so fluid on the boundary, or the fluid particles on the boundary, they stick to the boundary. But she uses inhomogeneous conditions at the level of the stream function. So there are caveats. She writes, the example described here can provoke displeasure for only one reason. It has been constructed for boundary conditions of type 18, which are for the stream function, but not for adhesion conditions. The examples presented here are interesting to me in that they refute the entrenched opinion on the naturalness for non-stationary problems of physics and mechanics of the class of solutions which have finite energy norm. Within the past decade, we've seen further progress for understanding non-uniqueness, which you can organize into, you might call them 2 programs. So the first is essentially this series of 3 works due to Jia, Sverok, and Guillaume, Vladimir Sverok with us today, which produced compelling numerical evidence, which produced compelling numerical evidence of non-unique Luray solutions. But at least the current state of the art is that does not constitute a rigorous proof. So I write there's no proof in quotes. I write proof in quotes because for the broader scientific community, people whose main business isn't necessarily mathematics, they might consider this numerical evidence as proof. And now we know that Luray solutions aren't unique. And in fact, when I was a graduate student and some of these works were coming out, I felt for myself, or I felt that, with this numerical evidence, we know something like the truth. Now, the truth is that they're not unique. I don't necessarily have to go try to prove anything about it, but
in what sense can one get numerical evidence without knowing it's a well-posed problem? Or what I have to calculate in.
Right, so that, right, there's a theoretical part that you have to do to convince yourself that this question can really be approached numerically. There's some kind of reduction you must do, and which I'll explain in a couple slides. I still like the questions. Yeah, please keep asking. So the second program has to do with what we're doing here in the special year. There were convex integration constructions due to Buckmaster Vickel, Cheskirov, and Lowell. So 3 of these people are here, maybe not in the room, but here for the special year. Also, this T should be on the bottom. And these constructions can rigorously prove the non-uniqueness of weak solutions of Navier-Stokes, but so far they cannot reach the Leray class. So these 2 programs are in some sense, in dichotomy. This can reach Leray solutions, but currently no proof. These are proven, but they cannot reach Leray solutions, to the best of our understanding. Anyways, so here's a theorem that we proved that was recently accepted. So this is joint work with Elia Brewer and also Maria Colombo, who's at EPFL in Switzerland. So we prove that there are 2 distinct suitable Leray-Hopf solutions to the Navier-Stokes equations. They have identical body force and they have identical initial velocity, which happens to be 0.
Is it on a torus?
And it's on the whole space, and in 3D. Okay, so one of the things we're going to do for the rest of the talk is understand the ideas that go into this proof, but we're also going to eventually we're going to move past this. We're going to talk about Euler. We're also going to talk about some other models in which non-uniqueness can arise.
Sorry, could you say one word how you think about the physical meaning of this non-uniqueness, or what physical phenomenon kind of shadows it?
By the end of the talk, I hope to, maybe I'll just be raising that question instead of answering, but yeah, that's kind of the question. Yeah. Okay, I want to introduce a notion that we'll be using, a notion of self-similar solution. So first thing I'm going to do is introduce these self-similarity variables. It's, in a certain sense, it's a change of variables. It does nothing. But sometimes when you change variables, you see things kind of in the right frame. So I'll define a new variable C. It's x over root t. It's kind of a dimensionless spatial variable. And tau is going to be log time. So I also write my velocity field u as 1 over root t of capital U. Capital U is seen in these new similarity variables as a function of c and tau. Similarly, you write the force as a 1 over t to the 3/2 capital F. So these capital letters, they denote what we call similarity profiles. So these are functions that are really best seen in the new variables. So you can rewrite Navier-Stokes in the new variables. And when you do so, you've essentially done nothing. Maybe you don't have any new insights. What you do find, though, is that in the new variables, the functions capital U, capital F, they solve an autonomous system. It looks a lot like usual Navier-Stokes. It has some additional terms. These additional terms come from the time derivative. So when the time derivative hits 1 over root t, and you pick up this minus the 1/2 term. When the time derivative hits c, you pick up this c dot grad c term. And like I said, it looks a lot like Navier-Stokes. And if you're doing this, then you're doing essentially what Jean Leray already did in 1934. He proposed that perhaps Navier-Stokes could have blowups that arise in a self-similar fashion. So he was studying or proposing what we call backward self-similar solutions. So these are solutions which, as you go forward as you evolve toward the singular time, they're kind of concentrating, they're kind of rescaling and concentrating into the origin. We're here studying the opposite. You start from time 0, then kind of these solutions, which are maybe initially concentrated, are spreading out in a self-similar kind of parabolic manner. So that the core of the solution kind of lives in this parabola in space-time. Okay, so far you've perhaps done nothing, but what I want to point out is if the similarity profile capital U is order 1 in time, smooth and decaying, basically satisfies smooth dynamics. Then in the physical variables, little u belongs to critical spaces. That is, it belongs precisely at the regularity threshold where you could maybe hope to find non-unique solutions. It's just beyond where you can prove uniqueness. So this reduces this problem of non-uniqueness, which is inherently irregular, can only happen in the presence of irregularity. It translates it into a smooth dynamical problem for capital U. Now you can study this object capital U. So for this new system, whenever you have an autonomous system, you want to understand its steady states. Those are one of the simplest objects you can think of to try and help organize the dynamics.
So what is autonomous?
This system, this law for evolving does not depend on time. Yeah. So you can look for steady states in the new variables. So these steady states, we call them capital U bar. They're known as self-similar solutions because in the physical variables, they're given entirely by their profiles at time 1. You know what they're doing at time 1, you can rescale them and see what's happening at all the other times. They're self-similar. So the picture proposed by Geospheric and further explored by Spheric and Guillaume is the following. Take some function A0, which is like 1 over x. It's self-similar. It should be -1 homogeneous, self-similar, and it's divergence free. And you construct initial data for this problem by you take A0, you multiply by a size parameter sigma for size. For sigma is 0, you can solve this equation uniquely. I don't want to say uniquely. You can solve this equation. The solution is 0. But what you do is you take the sigma parameter, you start growing it. And when sigma is small, there's a unique small solution in Navier-Stokes. It actually falls within basically by this heuristic, the nonlinearity is size sigma squared, the linear term is like size sigma. So when sigma is small, there's a unique small solution to Navier-Stokes, and it's self-similar. You can start increasing the sigma parameter and continue looking for self-similar solutions of Navier-Stokes. Now remember, in the renormalized variables, in the new variables, self-similar solutions are steady states. You can ask whether or not these steady states are stable or unstable. When sigma is small, they're stable. As you start increasing sigma, there's the chance that they might become unstable. And you can understand this by writing the linearized operator around these steady states. And now if the solutions do become unstable and maybe there's some bifurcation, so some new solutions emerge, then that will correspond to a loss of uniqueness. I'll have some pictures on the next slide actually, but you can prove a theorem, like a criterion for this non-uniqueness. This was done by Geospheric in 2015. It's roughly the following. Suppose you have a transcritical bifurcation or a Hopf bifurcation. So this corresponds to a real eigenvalue crossing or a pair of imaginary eigenvalues crossing. By crossing, I mean they go from stable to unstable. The real part goes from negative to positive. Then, upon truncating the solutions properly, there exists 2 distinct Lurie-Hopf solutions with identical compactly supported initial data. 0 force, there's no force, and the initial data is like 1 over x at the origin. So this is a criterion. If these bifurcations occur, then you can prove non-uniqueness of Lurie-Hopf solutions. But now you can look for these bifurcations on the computer. So that's what Guillaume and Spheric did in this paper, which you can find in the archive. They find that if you take a particular A0, which has a reflection symmetry across the z equals 0 plane, and you start increasing the sigma size parameter, then around sigma equals 292 or something, you'll find a bifurcation, which breaks the reflection symmetry. So what I'm drawing here, which you can find on Guillaume's website, you can in fact see videos of this bifurcation happening. This is just one component of the velocity field at time 1. These solutions are self-similar, so you only need to know what's happening at time 1 to know what's happening everywhere. This is one component of the velocity field. This is the symmetric solution. This is one of the non-symmetric solutions. as you can see, it's kind of this bit kind of is reflected up, and then there's another solution where it goes down. So from the same self-similar initial data, you can have at least 3 self-similar solutions emerging out of it. So here's just a piece of the spectral calculation so what we're seeing here, so this is sigma size parameter, real part of the eigenvalue lambda, we're just looking at the low-lying eigenvalues, which are close to crossing. You can see here that around sigma is just below sigma equals 300. The eigenvalue crosses.
Now, in what space with the linear operator have discrete eigenvalues? In a compact
Right.
domain?
So the what you can prove is that so there will be a central spectrum, but what you can prove is that a central spectrum is it's in a left half plane. It's real part of lambda less than -1/4. So the essential part of this, the essential spectrum is stable actually. So for instability, we just look at eigenvalues. Okay, there's these kind of bifurcations are not mere mathematical fancy. I mean, they're really motivated by bifurcations that occur in nature. There's a short video I just want to watch. So this is a Hopf bifurcation in flow around a cylinder. So at low Reynolds numbers, which let's just say at small speeds. Around a cylinder, so you flow past the cylinder. You can think almost like you know, there's a bridge that's being supported by poles, and there's flow past it.
Is it really two-dimensional?
Yes.
Well, the numerics are really 2D. Okay, so at small Reynolds numbers, there's a unique solution. It's steady. And it has these kind of characteristic recirculation regions behind the cylinder. So this here, the fluid is, I don't have to point out with the mouse. I can point out with this. Here, the fluid is recirculating here, and then these streamlines are kind of go around the body. And what you find is that at some critical Reynolds number, the solution that you see is no longer the steady solution. It's this time periodic solution. So that's a hallmark of a Hopf bifurcation. So this solution, by the way, still exists. This steady solution, when you increase the Reynolds number, it still exists. It's just not the one you see because it's unstable.
What's the intuition for why there's a critical Reynolds number?
What's the situation for why?
What's the intuition for why is there a critical Reynolds number?
Well, we know that when Reynolds is small, everything's essentially linear.
Yeah.
And so we can say that at least for small Reynolds, you know, there's unique solution and things are stable.
Would you expect there to be actual like above this or below this?
Yeah. So at what happens at the critical Reynolds number is that, you know, when you study the linearization around the steady state, you'll see an eigenvalue crossing. In this case, you'll see a pair of imaginary eigenvalues crossing. To my knowledge, to the best of my knowledge, it's not proved that in this scenario that actually happens, but it's known. Okay. So these bifurcations, they really do occur, at least for steady Navier-Stokes. And the situation in the new variables, Navier-Stokes and these renormalized variables is similar. Okay, so I'm going about half as fast as I hoped, and that's totally fine. Let me say what we did recently. The difficulty with the picture we saw in the previous slides, which has no body force, it's kind of more of the ideal scenario of how you want to analyze non-uniqueness of these array Hopf solutions. That picture is difficult to verify analytically by hand. The objects are kind of non-explicit. You could maybe say something about their asymptotics at infinity, but you don't really have them in hand to analyze. But if you incorporate a body force, it adds enough flexibility to the problem to make these objects explicit. And in fact, from a certain perspective, you get to choose the object. This is because, from a certain perspective, any function solves Navier-Stokes equations. If you allow yourself a force, the force is the right-hand side that you get when you plug the function into the equations. So we allow ourselves the flexibility of a force to make these objects explicit and tractable. So this is a criterion that we prove in the paper. Suppose that there's some similarity profile, capital U bar, which is smooth and compactly supported and divergence free. And if you start rescaling this, you can form a self-similar solution out of this, like this. That's what we take as solution 1. Now suppose that it's linearly unstable in the self-similar variables. You have to go to the new variable. Suppose it's linearly unstable. Then in fact, you can promote this linear instability to nonlinear instability. There's a construction you can do, or there's an object you can find called the unstable manifold of U bar, and it contains trajectories which backward in time converge to the steady state. So if you think of them forward in time, it's kind of like at time tau equals minus infinity, there's you just have U bar, and then you can have solutions which kind of just emerge out of it, almost like emerging out of nothing. So these functions or these solutions on the unstable manifold in the new variables, in the physical variables, those constitute your other solutions. They give the non-uniqueness. The force comes entirely from the first solution when you plug it into the equations.
I forgot how it's still related to time.
Tau is log t. So whereas t is greater than 0, tau belongs to all the reals. So I want to present just some ideas in the proof, just a few slides about how it works. So this criterion is not difficult to prove. Finding this object U bar which satisfies the criterion is the difficult part, because you're trying to find this object which you get to choose, but it needs to be unstable for this kind of this weird operator. It's linearized Navier-Stokes in the new variables. But my claim is you can reduce this question to finding unstable steady states of 3D Euler. So 3D Euler, by the way, is not, that's Navier-Stokes where you draw the viscosity term. So the heuristic is the following. Here's the linearized operator. So it has this part, so this part comes from the time derivative when you change variables. There's the Laplacian. Here's the part that comes from the nonlinear term. You have this U bar, and you get to choose U bar. So you can increase its size. You can multiply it by a number beta. Just make it bigger. That essentially just makes it more unstable. And when you increase beta, this term seems to dominate, and these parts seem negligible. And so you can kind of convince yourself that maybe you can treat this as perturbative. So you can make this heuristic rigorous. That's what we do in the paper. Reduce the problem to understanding unstable steady states of 3D Euler. And what we find is that, remarkably, no suitable steady states of 3D Euler were known, at least known to us, that we could just use for our analysis. So a key component and the main difficulty of our proof is to construct them. And I don't discount that if we talk to the right fluid dynamicists, they might have a suggestion to look at this object should be unstable, and maybe you can prove it. But at least in the mathematical literature, and at least in terms of all the people I've surveyed and all the talks I've given about this, no one has had a suitable candidate object in mind besides the one that we use. So we can reduce the problem to a question about unstable steady states of 3D Euler. Two-dimensional steady states of Euler are much better understood. Let's start with those. There's an explicit class, the class of so-called vortices. And these are simply velocity fields whose action is to kind of swirl you around the origin. And how much you're getting swirled around the origin depends on how far you are from the origin. So these are vortices. And the study of vortices goes back to the earliest days of hydrodynamic stability, Rayleigh 1880, and before, but in terms of analysis, let's say. So we're going to use the following theorem of Vishik that was proved in 2018. He just proved in kind of colloquial language, there is a smooth, unstable vortex. We also observe that you can truncate this vortex so that its velocity field is compactly supported. You can keep it unstable. So this is one thing you might want to do. I'll tell a little bit of a story about this theorem in a few slides. So now you have this candidate 2D object. I want to say something else actually. Although this was only proven in 2018, the ideas for it go back to at least the German physicist, German fluid dynamicist Tolmin. I believe he was a student of Prandtl. The rigorous proof was only written down in full gory detail in 2018. So you have this 2D object. You want a 3D object. We're going to try to lift the 2D object into 3D. We'll do so by constructing a vortex ring. So vortex rings are real objects. Here's one. It's this little thing. This is a vortex ring of steam above Mount Etna in Italy. The way you construct it is, well, first you write everything in axisymmetric coordinates. These are coordinates which depend only on, so the functions only depend on the radius r and the radius r and z. And this 2D object that Vishik constructed, you essentially place it into 3D like this. And so, I mean, the real picture is revolved around the z-axis as well. And this is your ring. And you hope that as you do this, the resulting object is unstable. It was unstable in 2D, maybe it'll be unstable in 3D. There's one more thing you can do. You can introduce this parameter little l. Little l is the distance of this from this core to the z-axis. Little l is going to be large. So these vortex rings, you might call them vortex rings of small aspect ratio. Their study also goes back to the 1800s.
You take it large because it looks straight and locally.
Yeah, because the key observation is that when as you take r to infinity, or you take this parameter l to infinity, then the axisymmetric Euler equations without swirl formally converge to the 2D Euler equations. So maybe since I want to get to some of the other stuff, maybe just take my word for it. But you can use this once you have this observation in mind, once you have the 2D object in mind, the path forward becomes clear. You want to perturb the 2D object to the 3D object, and as you do it, you want to keep it unstable. So you want to say that the spectrum of the linearization for the 3D object is close to the spectrum of the linearization of the 2D object, and you can really do this. Okay. By the way, that's omitting very many details. That's the end of the proof. So, okay, there are 15 minutes left, and 3 topics I want to cover, so 5 minutes each. First, I want to say something about how Ellie, myself, and Maria came to work on that problem. I want to tell a little story, which is that in 2020, I was supposed to be starting a postdoc at the Kront Institute, but that was still in the height of COVID, and my wife and I decided not to live in New York City, but to come live here in Princeton, because we were both supposed to be in Princeton this year. And Camilo knew I was here, and he invited me to take part in a reading group that he was organizing on these 2 papers of Vishik. And together, these 2 papers from 2018 are over 100 pages, and people knew that they were important, but perhaps no one had really checked them in detail, really understood everything about them. And so we had this reading seminar in which we, over the course of some months, explained the paper to each other. And in the end, we wrote these 7-author lecture notes, which you can find on the archive, which will hopefully be of some service to the community. So what we do in the lecture notes is I should also say, in this process, we started noticing some similarities between work of Vishik and work of Jan Sferak. and we start to piece together maybe a somewhat coherent picture about what's going on. Okay, so what Vishik did is he solved the related non-uniqueness question, the 2D Euler equations. For 2D Euler, bounded vorticity is a uniqueness class, and there was an open question about can you weaken this? Is LP for large P also a uniqueness class? You can certainly find weak solutions there. Are they unique? And he was able to show that they're not. So this is what we spent some time understanding. There's another work, or two other works rather, on Euler non-uniqueness without force, and these are in some ways analogous to the work of Gian Sperak. Let me just explain it very quickly. So this is work of Brisson, Shen, and also Murray. So you can look for, you can try to solve this 2D Euler question about non-uniqueness with vorticity and LP with large P. You can also try to solve it with self-similar solutions. And so Brisson and Shen proposed some self-similar initial data of a very particular form. So it has the singularity of the origin, like r to the minus 1 over alpha. And alpha here we think of, you take it close to 0, so that the solutions will be near bounded. And then you can so on the sphere, this function phi on the sphere, you make it look like this. It's supported on these kind of wedges, and you can desingularize this initial data in two different ways. One is for every, at scale epsilon, just fill in this kind of region with epsilon to the minus 1 over alpha. A different way is to just cut out this region, fill it in with 0. When you do this, you put it on the computer, you see two very different behaviors. So these are the profiles of the solutions at time t equals 1. So the solution in which you fill in the center, it has this behavior where this core acts to kind of swirl these wedges start spiraling around. You see this kind of spiral. On the other hand, when you separate these two wedges, they spiral in opposite directions, and you see instead this. Okay, I want to summarize kind of in this little table what's known for Navier-Stokes and Euler non-uniqueness, at least by these kind of methods. So there are two kinds. Right now, there are two kinds of results. There are results without force, but with some kind of numerous or computer assistance. For Navier-Stokes, that's work of Gian Sperak. For Euler, that's work of Brisson, Murray, and Shen. There are also types of results with a force and without computer assistance. That's work of myself, Brewer, and Colomba. And for Euler, that's work of Vishik. Okay, for the remainder of the talk, I want to address two further scenarios, just mention them. I think it'll be food for thought. Two further scenarios in which we can make maybe better informed conjectures than we can right now for Navier-Stokes. So the first scenario has to do with non-uniqueness after a singularity formation. For Navier-Stokes, we don't know whether singularities can occur. The best we can do is start with some singular data and show that things become non-unique, but we're gonna think about this in the context of the complex Ginzburg-Landau equations, and also I want to talk about how non-uniqueness can potentially arise in the implicit limit. We're going to focus on vortex sheets. So what I'm going to try to describe is actually work of Vladimir that he started maybe in the late 90s, early 2000s. So consider this equation, complex Ginzburg-Landau equation. You can think of this equation as a viscous regularization of the cubic focusing NLS. That is, here's this term minus I epsilon Laplace U. This is kind of a heat term, and if Laplace is 0, that's nonlinear Schrodinger. So this particular complex Ginsburg-Landau equation, exhibits the same scaling symmetry as Navier-Stokes, has the same energy equality. You could also make some comparison between the inviscid systems, nonlinear Schrodinger and Euler. I don't know whether or not they're really surface level comparisons or not, but let's make them. They're both Hamiltonian systems. They have these conserved quantities. NLS has the mass, which is a sign definite quantity, and also the energy, which is a sign indefinite quantity, and which lives at higher regularity. Euler also has the energy, which is a sign definite quantity, and has the helicity, which is a sign indefinite quantity, which also lives at higher regularity. So complex Ginsburg-Landau, it has self-similar singularities, or at least, well, you might call it generalized self-similar singularities. So here we write this ansatz. U is given by a profile capital Q. Q is actually a radial function here, which you're rescaling in the same way that you would do for Navier-Stokes. So in the denominator, there's a 1 over root t. And here in front of the capital Q, there's a 1 over root t. But there's another factor, this factor here. So this is like root t to the minus I omega over kappa. What's happening is that as you approach the singular time, this profile Q, I mean, it's essentially, so this is a rotation in the complex plane. It's spiraling around faster and faster. This factor is associated to the gauge symmetry of the equations. If you have a solution U, multiply it by e to the I theta U, you get another solution. Okay, so you can look for solutions satisfying this ansatz. That's what Plekach and Sverok did back in 2001. They exhibited a countable family of these solutions. So for every epsilon, you have for every epsilon you also need to prescribe how kappa depends on epsilon, how omega and profile. So this is just a diagram of, here we have epsilon on the bottom. Epsilon is the viscosity parameter. Here's how kappa depends on epsilon, at least for some of these solutions they find. So here's one branch of solutions. This J equals one branch, and then there are kind of higher branches and branches I'm not drawing. So I want to, I mean, there are two interesting things I'll point out. So here where epsilon equals 0, this you'll find here a known solution of a cubic focusing NLS, a known generalized self-similar singularity. Then this branch it comes back down to epsilon equals 0 and kappa equals 0. And here this profile will look more and more like the ground state of NLS. So in fact, this branch is connecting two familiar objects from the NLS theory. Okay, so for complex Ginsburg-Landau, we know that singularities can occur, and you can even describe them in a fairly detailed way. And you know what the blow-up profile looks like. The blow-up profile, so what the solution looks like at the blow-up time, looks like constant times c to the -1 minus, or let's say x maybe, yeah, it looks like this. This serves as initial data for a potential continuation of the solution. And now you're in the situation that was studied for Navier-Stokes by Sverok and Guillaume. So you can look for non-uniqueness arising from this kind of data. You can study it on the computer. So here, these are the low-lying eigenvalues of the linearization around the profile of the self-similar continuation. And you find that for some values of kappa, you'll have instability. I'm a little low on time, so I'll just point you to this online lecture that Vladimir gave in 2020. You can find it on YouTube, Lessons from CGL. But after singularity, you can have non-uniqueness here. Okay, I want to conclude with the potential for non-uniqueness to arise in the inviscid limit. And we're going to focus on a well-known instability called Kelvin-Helmholtz instability. This instability isn't pure mathematical fancy. You can see it occurring in this cloud formation. So the solution whose stability you're considering is a so-called vortex sheet. So this is a solution of 2D Euler, whose vorticity is concentrated It's like a Dirac mass along a line. At the level of the velocity, above the line, the velocity is, the velocity is minus u/2 in this direction. Below the line, it's u/2 in this direction. So if you make a small perturbation to this object, then maybe at high frequencies, then you can find that these perturbations grow. And in fact, they form these very interesting large-scale objects due to an inverse cascade. Okay, this kind of region here, give it a name, it's called mixing layer. So I want to present briefly results of Thalberg, Beck, and Melibaev. So you want to study this object. The Euler equations don't really make good sense near this object. So instead, you regularize the equation. You study Navier-Stokes. You add some viscosity. Okay, and you want to study stability, so you should perturb your object. So let's add random perturbations of amplitude epsilon to the initial data. Now you have two parameters to play with, mu and epsilon. What will happen if you send mu and epsilon to 0? Well, first of all, if you send epsilon to 0 first, then it's like you're making no perturbation. You're just solving Navier-Stokes with vortex sheet initial data, which you can do. On the other hand, if you send mu to 0 first, then the problem doesn't really make sense. You can't really solve the equations. So you send them to 0 in tandem. In general, you could choose some relationship between these, but the relationship that works is this linear relationship. Where you find the limit is a non-trivial measure of solutions with seemingly universal macroscopic properties. So your measure does not condense to a Dirac mass measure on the vortex sheet. That's what I mean by a non-trivial measure. This is sometimes called spontaneous stochasticity. In the paper, they study various ways to quantify it. One is by the separation energy. So what's the separation energy? So you take one random solution, take another random solution, subtract them, calculate their energy, average over all samples. So this separation energy, as you take mu and epsilon to 0, you find that it has some initial transient exponential growth phase, and then it consistently settles in to this power law growth. So as you take mu and epsilon to 0, you're not going to see this transient region anymore. You're just going to see the power law growth. And in particular, you do not see nothing. You can also quantify how this mixing layer grows. You can find a similar statistical quantity. It grows like alpha ut. Alpha is some dimensionless constant, and pretty robustly you find that the mixing layer is growing like this, and alpha settles into a very particular alpha as you take epsilon and u to 0. So there are convex integration constructions that can produce weak Euler solutions that exhibit something a lot like this, exhibit a mixing layer type behavior. I'll just mention these works, also works of Fargo and others. The precise relevance of these weak Euler solutions, whether they arise in a particular regularization procedure, whether they arise from, and whether this regularization procedure captures more essential physics, remains to be clarified. All right, this is the last slide. I appreciate you guys bearing with me as I take all the way up to the allotted time. I want to conclude with a quote from Lorenz. So all the non-uniqueness that we discussed today, it arose due to instability, very, very extreme forms of instability. The possibility of this was anticipated already by Lorenz in 1969. He wrote the following: "It is proposed that certain formally deterministic fluid systems, which possess many scales of motion, are observationally indistinguishable from indeterministic systems. Specifically, that two states of the system, differing initially by a small observational error, will evolve into two states differing as greatly as randomly chosen states of the system within a finite time interval, which cannot be lengthened by reducing the amplitude of the initial error." So what Lorenz was referring to was a more extreme version of chaos than what people normally think of as chaos, which is mere sensitive dependence on initial conditions. This is what Tim Palmer calls the real butterfly effect. The real butterfly effect. So like I said at the beginning of the talk, I mean, the title of the talk is more bold than we can really show, but from in these case studies that we've done today, it suggests to me at least that we should think carefully about the conventional wisdom surrounding the Navier-Stokes equations. There may be regimes in which this non-uniqueness is not really a fluke, but is something real. Our understanding of this concept, at least from the perspective of rigorous PDEs, is in its very early stages. So I hope others here will join me in thinking about it and discussing it at tea. Thanks.
Thank you very much. I'm sure there are lots of questions.
I just want to say, what is this real butterfly effect? I didn't understand what you meant by that.
This real butterfly effect, what he's referring to here is the idea that, so at least in the presence of many scales of motion, which mathematicians, we should read this as irregularity. Basically a kind of predictability horizon that there's really, you really can't predict the motion. You can maybe predict large scale, maybe the large scale macroscopic quantities are maybe to understand those, it's irrelevant what exactly is going on. But in terms of describing the exact motion down to the smallest scales, something like it's impossible. That's how I read it. But actually, Theo and Sam know more about this than I do, so they'll be happy to discuss. I volunteer them to also discuss it.
When we are speaking of using computer, how does one make sure that it's meaningful if one has no a priori theorem of uniqueness?
Right. Yeah. So that's at least at the regularized level. That's why you do need to regularize to make sure that you study something that's well posed. So the kind of, I think the general principle, at least in my head, is that you should regularize by more fundamental physics. You should go kind of up a level in the hierarchy of models. And that's actually why at the beginning I wanted to remind ourselves what we're when we work with Navier-Stokes, what we're kind of forgetting about.
Doesn't the computer sometimes add some viscosity also?
Yeah, like yes. So how should the numerics be done? Carefully. Yeah.
Great. I'd like to thank the speaker again for a fantastic lecture. Thank you.